to complete our discussion this time about the case NF is equal to NC plus 1. Okay, so now that we've seen it so many times, we will just remember, right, that the R charge of Q, which is the same as the R charge of Q tilde, was I think 1 minus, as many times as I've seen it, NF by NC? NC by NF? NC by NF. Okay, and therefore the R charge of, this is the true R charge, okay. The R charge of psi q, which is the R charge of psi q tilde, is equal to minus NC by NF. Right, this we will, everything else is obvious. This is the one thing to keep in mind. Right. Okay. So we were discussing the case NC is equal to, NF is equal to NC plus 1. You remember we talked about the gauge invariant operators in this situation. There were the MIJs as always. And then there were these BI operators, which were the baryon operators, which were epsilon I, then I1 to INC, epsilon A1 to ANC, Q A1 I1, Q ANC INC. Right? It was the gauge invariant baryons made by all quarks except the ith quark. Right? And we discussed last time the relationship between these M's and the B's classically. The relationship was, so note that M1 index is an index of SUNF for the quark, for the Q type fields. The second index is an SUNF for the Q tilde type fields. And we saw that BI Mij was equal to 0. Mij Bj was, B tilde j was equal to 0. And we also saw that the inverse, the minor, so M inverse det M was Ij was equal to Bi Bj tilde. And really I should be, yeah. So I'm consistently keeping the indices of M down, B up, and M inverse up. Okay? You remember that we discussed last time that Seiberg's proposal for the physics of this system was that there was a superpotential in this theory proportional to det. Sure. Yes.
If you dot M with M inverse,
yes.
You should get identity.
You should get identity. Good. An identity has one lower, one upper, so that is identity.
Yes. So now in this equation you wrote M inverse Ij, Bi B tilde j.
Yes.
Dot with Mij, both sides.
If we dot with Mij, yeah, we would. You're saying here we get here we should get 0, but here we get identity, and the resolution is that det M is 0. You see, do you remember?
Yeah.
Det M was 0. M inverse was ill-defined.
Yeah. Okay.
It was this, the minor that was. Yeah. Okay. Excellent. Other questions or comments? Excellent. So the idea was that there was a superpotential proportional to this object here. W proportional to this. There was a 1 over lambda to some power to make up dimensions. Okay, and a superpotential proportional to this object here. We saw that varying the superpotential with respect to B and M produce those classical relations. Okay, so Seiberg's idea here was that this Thank you, B tilde. was that this relationship that was absolute on the classical moduli space of vacuum, okay, gets sort of floppy, comes from a superpotential, comes from fields that fluctuate away from the way that classical fields can fluctuate. And a superpotential gives you this condition. Okay, this is the idea. Now, in the last class we just presented this idea and didn't study any checks, right? So now we talked in the last class about how the R symmetries worked out. The superpotential has R symmetry too. In fact, if you just take the det M part of it, it's just the Affleck-Seiberg superpotential for this case. So it has the right R symmetry. This other term also has R symmetry too, so it's a possible modification to that thing. There would be other possible modifications. Okay, and the argument was that this was the right one. Okay, so now we're going to study various checks of this proposal. Okay, the first check we're going to study is the check obtained by giving the nth field a mass. Okay, so suppose we consider the superpotential W is equal to 1 over lambda to, okay, this power, in fact, I'll keep track of that power. This power that appears here is this B0, which is the same as the coefficient that appears in the beta function, which is 3nc minus nf. B0 is equal to 3nc minus nf. This is notation, and this is here the power that appears here. Now, of course, in this particular case, we could simplify it, right? Because nf is equal to nc plus 1. So we would get to 2nc minus 1. Okay, that's the power that appears there, but we will often use this notation B0 for various other cases as well. Okay, so we have this W is equal to det M minus Bi Mij B tilde j, and we're going to perturb this by adding a mass. Okay, so just so that there aren't too many m's on the board, I'll call the mass x. Okay, and this is a mass just for the QNF field or NC plus 1th field. Okay, clear? Fine. So that's the same as adding this thing here by definition is M, NC plus 1, MC plus 1. So this is similarly adding a superpotential M, NC plus 1, NC plus 1 to this problem. Okay? So by adding this mass, and if necessary making it large, okay, we want to see what effect we get when we integrate out this massive field. Okay, so let's integrate out the massive field. In order to do that, so when we do that, of course, we're going to go down to a theory with only NC quarks. Okay, so let's see what the equations of motion are that we get for all the fields that we will not have in the low energy problem. Okay, so what are the fields that we will not have in the low energy problem? Well, in the low energy problem, we will not have the M fields with any NC plus 1 in it. So we will not have M NC plus 1 NC plus 1. We will not have M NC plus 1 I. And which baryon fields will we have in the low energy problem? Well, the only baryon field we will have in the low energy problem is B NC plus 1. because the baryon has to be made out of only the low energy quarks. So the guy that's excluded must be Nc plus 1. Okay, so all BI's also we want to integrate out. Okay, so one to integrate out all fields involving heavy particles. So one to integrate out M Nc plus 1, Nc plus 1, M Nc plus 1 I, M I Nc plus 1, and M Bi, where I refers to all indices that are not Nc plus 1 to Nc. Okay? So let's just work out the equations of motion for all of these fields and see what happens. Okay. So let's, to be consistent here, let's say that this was alpha, this was beta, where beta now runs from including over I and Nc plus 1. Okay. So let's do these fields one by one. I are the indices, flavor indices going from 1 to NF, to NC.
What's the range of alpha?
Alpha runs from 1 to Nc plus 1. Right? So the flavor group of the high energy theory, alpha is a flavor index for the high energy theory, I is a flavor index for the low energy theory. Okay? Excellent. So let's do the easy ones first. Let's do B I. So we integrate out Bi, that tells us that Mi beta B tilde beta is equal to 0. Right? Then we integrate out B tilde. B tilde, that tells us that B alpha M alpha I is equal to 0. Okay, so we've Bi and Bi tilde. So these two are done. Okay, now let's integrate out the M's. Okay, so let's start with M Nc plus 1, Nc plus 1. Okay, that tells us that, in fact, let's do this guy last. It's the most interesting. So let's do M Nc plus 1 I. Okay, so if we do M Nc plus 1 I, what do we get? When we vary determinant of M, we get M inverse Nc plus 1 I times det M. M inverse Nc plus 1 I times det N. And when we vary this object here, we get B I, yeah, B Nc plus 1 B tilde I. Okay, similarly, M inverse I Nc plus 1 times det M minus Bi B tilde Nc plus 1 is equal to 0. Okay, and finally the most interesting of these equations, which is the one with respect to M Nc plus 1 Nc plus 1. Okay, that when we vary, we get this kind of term from those guys. So we get M inverse Nc plus 1 Nc plus 1 det M. Okay. M inverse Nc plus 1 Mc plus 1 det N minus B Nc plus 1 B Nc tilde Nc plus 1 plus X is equal to 0. Okay. Now, one solution of all these equations, and presumably it's the unique solution of these equations, goes as follows. Bi is equal to b tilde I is equal to 0, and M is diagonal. Is a matrix alpha times M low, let's say. Okay. Why does this solve the equations? M is block diagonal. Yeah, alpha 0, 0 and whatever it's here. Okay? This is the NC plus 1 guy. You understand, right? Why does it solve the equations? Well, let's look at this. M inverse, if it's block diagonal, clearly has no diagonal elements, so this guy vanishes. But this guy also vanishes because there's a b tilde I. Okay, similarly it solves this equation. Okay, now this equation is solved because M, anything with an because b tilde I, because b tilde I is 0 and Mi NC plus 1 is 0. So this runs over NC plus 1 elements. NC of them are 0 because b tilde I is 0, and the remaining one is 0 because Mi NC plus 1 is 0. It's block diagonal, right? So these equations are all solved by this ansatz, and I haven't looked very carefully, but I presume this is the only solution of these equations. This equation? Yes, that's what remains. What?
Also, you said determinant of M is 0.
We will get, you're saying?
No, you said determinant of M is 0.
Yeah, determinant of M was 0 in the case where, at least without the deformation. We will, right, you see, there is this M inverse and determinant of M. So really what this should be is the minor. Okay? So really what this is just determinant of this guy. Okay? So let's write down this fourth equation as Kanu was saying. You know, writing it this way is just because it's inconvenient to write the word minor. But this is what you get by varying the determinant with respect to the nth element. And it's clear that that's the determinant of this line, right? Okay, so this guy is det M low minus, and what was this from the point of the low energy theory? Well, it was just B and B tilde, right? What in the previous class we called B and B tilde. Okay, minus B tilde. Now we have this lambda to the power, what was it? 2nc minus 1. Is equal to minus x. Okay, now let's take this up here. This becomes det of M low minus B tilde is equal to some number order 1, some sign doesn't matter, times lambda to the power 2nc minus 1 times x. But you remember that by the decoupling relations, this was precisely lambda low time to the power 2nc. And the way that works is that 2nc is that B0 factor that appears in the beta function for the low energy theory. And 2nc minus 1 was the B0 factor that appeared in the beta function for the high energy theory. And these two things matched at scale m. So that was the statement that lambda L to the power 2nc was equal to lambda I to the power 2nc minus 1 times mass. You remember we've been through this kind of argument previously. And so this is exactly the relation that we know to be correct for the theory at nf is equal to nc. Because in that theory we know that there's a constraint which is det m minus bb tilde is equal to lambda, some number times lambda to the power 2nc. Okay? So you see that this, that one of the really convincing pieces of evidence for this proposal is that it reproduces what we already know to be correct at one lower level. This is usually how evidence is built up for dualities. You know, evidence is built up for dualities with some checks, but then there's a web. You know, if this is true, it implies this, which we also have good reason to believe is true. And consistency of that web gives you much more evidence in every duality than you would have in any one without these interconnections. Okay, so it's a story that hangs together. Okay, yeah. Of course, none of these dualities have been proved. Far from it. And none of these statements really are proved. Okay, Affleck-Seiberg superpotential, I say, is a proof. Maybe NF is, after that, the educated guesswork that hangs together, in my opinion. Okay, which is, of course, a very useful wave function. Okay, excellent.
You were saying that writing down the low energy theory was, that part you were saying that it's...
So far, all we're doing is trying to write down the low energy theories. Yeah. Here, for instance, we made a proposal. Proposal passes many checks. So almost certainly it's correct, but it's too much to say.
Solution.
For the superpotential.
Yeah, okay.
But it's too much to say we've proved it, right? At least in my opinion. I don't think even Seiberg would say he's proved it. It's given almost certainly correct.
You are saying the Affleck-Seiberg is a proof because it follows from holomorphicity.
Because it follows from holomorphicity, symmetries, and there was one weak point which was, is the coefficient of it 0 or not? And that you'll explain to us in your instant-on lecture. We can do a calculation. So that, we've really computed. Even there, are we totally sure that that superpotential could not arise in the presence of massless quarks? Massless gluons, sorry. I know we think it's unlikely for all the reasons we've gone through in class, right? Usually these things give rise to singularities in descriptions. Are we totally sure that that would happen? Okay, I don't feel that any of this really any single fact could not have been falsified if you were very creative in attempting to find scenarios where it may not be true. But put it all together, it becomes like a conspiracy theory, right? For it to be untrue. Okay. Okay. Excellent. Now, let's move on. So we've got one nice check, right, of this proposal. That is, it reduces to what we knew to be, or we have other good reason to believe was true at NF is equal to NC. But let's see other independent checks of this proposal. That's actually quite a beautiful, independent, dramatic check. And that is by anomaly matching. Now I want to explain to you what I mean by this. I was alluding to this at the end of the last class, but I want to say this more clearly now. You see, this moduli space, as we discussed at the end of the last class, has a very symmetric point. It's b tilde I is equal to bi is equal to mij is equal to 0. Okay. Now, let's say we're at this, this point, And we want to ask, what are the massless fields around this point? But look, the superpotential here has no quadratic terms. Right? M is some matrix, which is at least, well, some big enough matrix because it's number of flavors, and number of flavors is number of colors plus 1. Number of colors can't be 1. So at least 3 cross 3 matrix. Okay, so that thing is at least cubic, usually more. And this object here is cubic. This tells us that at this point, all fields are massless. So if we want to compute the contribution from massless fermions in this effective low energy description, all the fermions contribute. The partners of M and the partners of B. Okay? Now this is quite dramatic because you see, this is testing the key idea of Seiberg's proposal. That is, these fields, which classically were constrained. There just weren't so many fields in the problem, classically. Quantum mechanically are independent fields which are free to fluctuate, subject to a superpotential. The superpotential here is so weak at this point that it makes all fields massless. So if this proposal is correct, then the anomaly matching condition should receive contributions from all these off-shelf configurations. You know, these B's and M's fluctuating as independent fields. So it's a very dramatic check of this idea. Yeah, it's really checking the key point. Okay, so let's check it. Is this clear? So first, what symmetries are preserved by this vacuum? Everything. SUNF times SUNF times U1 baryon times U1R. Okay? And so now here we can check basically everything. Okay. So let's list what we're going to try to check. We're going to check SUNFL squared. Okay. Now, as we've seen before, if we put one U1 baryon, we will get 0. Okay, because the contribution from Q and Q tilde will cancel. But we can put one U1R. Okay. Similarly, we can get SUNR squared times tilde 1R. Then we could get U1 baryon squared times U1R. And we can get U1R cube. Let me see if I've missed anything. Yeah. Wait. Oh, wait. I'm sorry. Despite giving you the argument that we should not consider the U1 baryon, actually we should. Because you see, we've got two SUNFs. So if you put SUNF left square, then the Q tildes will not contribute because they are uncharged under SUNF left. So in the previous case, we didn't want to consider things that were linear in U1 baryon because we were only keeping the diagonal, because our symmetry was only the diagonal combination of SUNF times SUNF. So the Q's and Q tildes behave identically under that SUNF. Okay, so there's one more we want to check. We can check SUNF left square times U1 baryon. Now, really, this is going to be the same check as this. I'm removing this, okay? So we want to check SUNF left square times U1 baryon, just writing the independent checks. Okay, then there's SUNF squared left squared times U1R, U1B squared times U1, and I think these are the four independent ones. Let me check. Yeah, that's good. Okay, so now let us start filling out our table. Okay, there's UV and there's Zia. That will not contribute because the U1B will cancel. You see, anything in which, for which under the symmetries the Q's and Q tildes behave identical will give you 0 if it's linear in U1B. Okay, Q's and Q tildes have exactly the same U1R charges. Exactly, because SUNF was different from SUNR. Right, so this one can give you something, something non-trivial. Okay, and now so let's go ahead and fill out the columns. Okay, let's start with this guy. Let's give us a little more space. Fine. From the point of view of the UV, we have SUNF squared. Okay, now the quarks were fundamentals under SUNF. The Q's were fundamentals under SUNF. According to our rule, that contributes a 1, but there were NC of them. Okay, so that contributes an NC. So let's see, this is the contribution from psi. That contributes an NC, and then each of them has a U1 baryon charge, which is, was it minus NC by NF? That's SUNF L square. SUNF L times SUNF L. Is this clear? Right? We get one factor for NC because it has, there are NC different colors as far as this symmetry goes. And another factor of NC by N minus NC by NF because that's the R charge of each of these size. Okay, now you can ask, what about psi tilde? Well, that's 0. Sorry, U1B. Okay, so U1B, then that's 1. What about psi tilde? Well, that's 0 because it doesn't transform under SUNF left. What about lambda? 0 because it doesn't transform under SUNF left. Okay, great. Now let's look at these fields. Here what we have are the fields M, Bi and B tilde j. Okay. Under okay. So we want SUNF left squared times U1 baryon. M is uncharged under U1 baryon, because M is a bilinear of Q's and Q tildes, and Q's and Q tildes have opposite charge under U1 baryon. So M's don't contribute. Okay, the only fields that will contribute are either B or B tilde. Okay, now B tilde is uncharged under SUNF left, so only B contributes.
Baryon charges are opposite. So
What?
baryon charges.
But at the moment we're doing SUNF left. It doesn't matter whether the baryon. Under SUNF left only B contributes because B tilde is uncharged under SUN and right. Okay, so there's only one field that contributes here, which is psi B. Okay, so now we need to know the baryon charge of B. But the baryon charge of B is same as the baryon charge of Q times NC. Right? Because it's a product of NC different quarks. So baryon charge is NC. Okay, and it's in the fundamental of SUNF left. So we get 1 times NC. Is this clear? 1 because SUNF left square contributes 1 in fundamental. Here there was no enhancement because there were many colors. There were no colors. These are all signets. But just the baryon charge itself is NC. Clear? Okay. Got it. Let's move on to SUNF squared times U1R. Since we're doing SUNF squared, once again, only size contribute. They contribute 1 times NC because SUNF squared, fundamental contributes 1. NC because there are NC colors of them. And then into minus NC by NF. Again, the contributions are entirely from psi because nothing else is charged as under SUNF. Yes? There are NCBs, but they transform in the fundamental. There are actually NC plus 1Bs. And they transform in the fundamental of SUNF. So that is taken into account in this SUNF. That they are fundamental under SUNF, we've taken into account in this one. Go on. There are NC size, we took into account the 1 because there were NF, that 1 was fundamental under flavor group. But in addition, they were charged under color. Color is not part of this anomaly thing, so each color index is a separate contribution to the triangle diagram. Okay? Whereas here the B's are not charged with color, they gauge invariant. Okay? So their contribution is only from the indices we see. Okay? Perfect. So, is this clear to everyone? 1 into NC into minus NC by NF. That was SUNF squared times U1R. Okay? Now, what about here? Once again, the only field that is charged under, well, no, now we have to be careful. Okay? Because there are 2 fields charged under SUNF, namely M and B. Okay? Both of them carry R charge. Okay? M carries the R charge of twice minus 2 NC by NF. And B carries R charge minus NC square by NF. Because B is a product of N Qs. Okay, we have to be, no, sorry, I got that wrong. We should multiply for the scalars and then subtract, add. Let me work out the R charges. Psi M, okay, that, I got them both wrong. Psi M, so let's first work out the R charge of M and then of its psi. Okay, M carries charge 2 into 1 minus NC by NF. Because it's twice the charge of Qs. Okay? And then, therefore, psi M carries charge, has charge 2 into 1 minus NC by NF minus 1, which is equal to 1 minus 2 NC by NF. This is the charge of psi M. Minus 1 because we're moving to the fermion component. Theta, remember, carries R charge 1. So if the bosonic component carries this charge, then the fermion component carries R charge 1 less. Because the whole superfield carries that R charge. But theta carries R charge 1. Is this clear? So this is the R charge of M, of psi M. And let's do the same thing for B. The R charge for Bi, so I really should be writing R of this. R of this. So the R charge of Bi is equal to Nc into 1 minus Nc by Nf. Okay? Which implies that the R charge of psi b is equal to Nc minus 1 minus Nc squared by Nf. Is this clear? Okay. Okay, so now we've got a pretty non-trivial kind of thing. So let's work out what we're going to get here. Let's first do it. Yeah. So first let's do the M's contribution. M is fundamental under SU NF. But there are NF different M's because it also has an SU NR index. Okay? So we're going to get the contribution 1 times 1 because it was fundamental under SUNF. Okay? Times NF because there were the SUNR indices that are going along for the right. Okay? Times the R charge of this guy, which was times 1 minus 2 Nc by Nf. Clear?
But in the first one, that was also SU NFL square, right?
Which one? Sorry, which one? This one?
The first one, column.
The,
First one of the table.
here.
That is also SU NFL square, right?
No, that came from a psi, which is fundamental under SUNF and fundamental under SUNC.
You just said M has this charge like 1 times NF under the SU NFL, right?
See, there are two SUNFs. There's SUNF left and SUNF right. This SUNF, this M, came from the fact that M was an object Mij. The fact that it's fundamental under SUNF left tells us it's 1. The fact that it also has an SUNF right index, okay, gives us this NF.
Yes, but we are not considering SUNF right, right? We are only considering
Only SUNF left. Therefore, SUNF right is just a multiplicity index. Let me say it again. Mij is bifundamental under SUNF times SUNR. We're not considering SUNR at all. So therefore, Mij consists of NF different fundamentals of SUNF.
Okay, so same thing should happen in the first case as well.
No, I mean similar, but there it was psi IA. Right, the field, the UV field was psi IA, where this is a flavor index and this is a color index.
In the IR case,
So just tell me which line you're talking about. This one?
there also we should consider
This one? This line?
we should only consider
Now there the field was BI.
not MIG.
No, Mij was uncharged under U1 baryon.
Okay, so that's why it did not.
That's why it did not play a role.
It's 0 multiplying.
0 multiplying whatever. Right? This is the first time we're considering the contribution of Mij. Clear? Excellent. Excellent. So let's keep going. So is this clear? It's NF times 1 minus 2 NC by NF. Okay. That's the contribution from M. Now let's look at the contribution from B. B under SUNF is just a fundamental. Okay. So we will get 1, no extra multiplicity index. Okay. Times its R charge. Times NC minus 1 minus NC squared by NF. Okay. Now we're looking like it's in miracle territory, right? We have to reach minus NC squared by NF. Let's see. So this is NF minus 2NC, okay, plus NC minus 1 minus NC squared by NF. And NF is NC plus 1. This cancels. Ah, thank you. Yes. So these three cancel. All four cancel, yes. Yeah. All four cancel. Thank you. Because NF minus 1 is NC. So this is 2NC minus 2NC. So it's 0, and then we get minus NC squared by NF. You see that already, you see from the level of calculation that this is not happening in a trivial way. The first one was happening in a trivial way. Whether you said there were NC fields or one field with charge NC, it sounds like bookkeeping, right? More or less the same calculation. This one, not very convincing check is what I mean. This one's pretty convincing check. Many things have to come together. So minus NC C squared by NF. I'm not even keeping track now of, or maybe I should, just since this is all being recorded, since we've worked it out. So what have we got? We've got that from psi m we have NF minus 2NC. From psi b we have NC minus 1 minus NC squared. Okay, wonderful. Let us keep going. Let's go here. Let us keep going. So we want u1b squared times u1. So let's work this out first from the uv. Here lambda doesn't contribute because it carries u1b equals 0. So the contributions come from psi q and psi q tilde. Contributions from these two are identical. Okay, because u1b is squared. Here the contribution is simple. This was u1r. We get 1 from u1b squared times minus nc by nf from the r charge times the multiplicity factor. Now the multiplicity factor is nc times nf and times 2 because there's q as well as q tilde. Okay, so times nc nf 2 nc nf. So total this becomes minus 2 nc square. NF because there are nf different q's. As far as these u1 charges are concerned, there are nf times nc different q's, each of which carry these u1 charges. Colors. Okay, similarly with the q tildes, that's why the two. Clear? Okay. Now let's do the IR. U1 baryon, M doesn't contribute. B contributes. Okay. B contributes. It carries U1 baryon charge, which is minus NC, minus NC squared by NF. No, I'm doing the same mistake again. It carries this one. This is the baryon charge of B.
No, this is
You're right. Thank you. I'm making many mistakes. Baryon charge of B is just NC. Okay. So baryon charge is, so I'm writing it down here. So the contribution of B is NC square because baryon charge. Now, there are NF different Bs. So NF, that's a flavor index, that's a multiplicity index. And the R charge of B is this guy. Okay. NF NC squared into NC minus 1 minus NC squared by NF. Okay. This times 2 because B tilde contributes exactly the same. Okay. Now how can it work? So let's see. So we have 2 into n, multiply the NF through NC squared into NF NC minus NF minus NC squared. Okay, that's 2 into NC square. Let's take the NF NC into minus NC square. So that's just a minus NC, right? That's a plus NC. So it's NC minus NF, which is equal to 2 into minus 2 into NC square. Which matches. Okay. So here the contribution was entirely from psi B. Yeah? And psi B tilde. And it was minus NC squared and minus NC squared. What?
We considered the NF there
because there are NF different B's.
Because of the U1 thing.
No. The U1 baryon charge for each B was NC. That is the reason there's NC square. Baryon charge square. But the number of B fields was NF. Right? Any index that does not appear in the symmetries we're considering is a multiplicity index as far as the one loop diagram goes. We just have to count how many such fermions are running. Is this clear? You know, all we're doing is computing a one loop diagram with fermions running. And if there are many different fermions, each of them contribute equally. Okay? So there's the fermion for psi, for B1, there's a fermion for B2, there's a fermion for B3, and there's a fermion for B up to NF. Each of them contribute, that's why the factor of NF. Is this clear? Okay, excellent. Finally, let us look at this U1 cube. U1 R charge cube. This is the most painful of the lot because every field carries R charge. Okay, so let's do both the UV and the IR, you know, on this blackboard. Okay, so let's look at the UV. There's psi of Q, there's psi of Q tilde, and there's lambda. All three contribute. Okay, psi of Q and psi of Q tilde contribute in an identical manner. So psi of Q and psi of Q tilde contribute like 2 NF NC. This is the multiplicity level because there are NF flavors and NC colors, and there's both Q and Q tilde. Okay? Then we want the U1 charge, the baryon charge of, the R charge of one of them cube. So we get minus NC by NF, right? NC by NF whole thing cube. What? the static on my mic. I'm sorry. Is this better? Okay. So everyone got this argument here? 2 NF NC into minus NC by NF, the whole thing cube. Okay, this is from the Q's. This is the contribution from psi Q plus psi Q tilde. Then there's the contribution from the gauginos, lambdas. Okay, how many gauginos were there? NC square minus 1. Carry R charge 1. 1 cube is 1. So that's it. Okay? So the UV contribution is this. Let's simplify it. So that tells us that it's total number of powers of NC is 4. Total number of powers in the NF in the denominator, so minus 2 NC to the power 4 NF squared plus NC squared minus 1. Now maybe we want to, I'm just leaving it here. Maybe at some point we'll simplify. Maybe at some point we'll simplify. It doesn't look like anything particularly nice. Okay, this is the UV contribution. So psi q plus psi q tilde, this was minus 2 NC to the 4 by NF square, and lambda was NC square plus 1. Total was minus 2 NC to the 4 by F square plus NC square minus 1. Okay, now for the IR. For the IR, B's and B tildes behave the same. Okay, so B plus B tilde, psi B plus psi B tilde. Okay, multiplicity factor 2 NF, because the NFBs and NFB tildes. What was the R charge for B, for the psi B? NC minus 1 minus NC squared by NF. Okay, we need Mathematica here. Okay. Okay, so this is psi B plus psi B tilde. What about psi M? Okay, well, first, how many M's are there? NF square. So plus NF square. What is the R charge for psi M? 1 minus 2 NC by NF. And that's it. Clear? Okay. Now maybe we need a little cleverness somewhere. Let's first take this and sort of simplify. This term?
In the first term.
Huh? In the bracket. First and last term. Good. Excellent. So Chintan's pointing out that we do this 2n, and now we'll write NF NC minus NC squared, so that's just NC. So NC minus NF divided by NF cube, but NC minus NF is minus 1. Okay, so we have 1 and we've got a minus sign here, cube. So this term is minus 2 by NF square. Not bad. Okay. What about this guy? So it was NCNF minus NC square. So NCNF, but NF was NC plus 1. That was minus NF. Right, so it was an NC minus NF. Okay, therefore minus. Okay, now what about this guy? Okay, let me just put the denominator plus 1 by nf into nf minus 2nc, the whole thing cube. Okay, I want minus, okay, minus nf. Okay, let me just open it out. Let's see. Is 1 minus nc the whole cube. Correct. Is 1 minus nc the whole cube. Yeah, I'm not, fine. Let me write that as 1 minus nc the whole cube. Fine. Yeah. Let's keep nf's only in the denominator. Okay. So we have minus 2 by nf squared plus 1 by, say, nf. Well, okay. 1 by nf into 1 minus 3 nc plus 3 nc square minus nc cube. Right. So let's see. There are the terms here that are order nc square, and there's a term of order 1. So let's get them. It's a pain, I hope it's working. Minus 2 by nf square, and I'm just making this also nf square. Minus 2 plus nf into 1 minus 3 nc plus 3 nc square minus nc cube. Okay. So it's minus 2 plus nf minus 3 nc nf plus 3 nc squared nf minus nc cube nf by nf square. Now, if we, for the top, so goal, the numerator should be minus 2 nc square plus nc to the 4 plus nc squared nf squared minus nf squared. This is what we want to check. Right, if we just take nf squared. Which one, sorry? I'm sorry, here?
All the way up to the second line.
This one was wrong. This was wrong?
Yes.
Let me check. This was nfnc minus nc square. Nf was nc plus 1. So we get nc minus, we get nc square minus nc square and plus nc. Yeah, and then this was minus nf. It may be working. Okay, you're saying it's working. I'll just check it as well. So the goal is, this was the UV answer. Diksha, are you convinced? Yeah. Okay, excellent. So this is the UV answer we want to get. This is the IR answer we've got. The denominators are the same. We just have to check the numerators. Okay. So first, the things that are of order nc to the 4. And this 3 nc to the 4 minus nc to the 4, so that's okay. So let's write that as nc square minus nc square. So that's no. This was NC to the 4, then how is it matching a 2?
It is NC square and F square, so that will be
Where was NC square and F square?
in the middle.
Ah. Here? NC squared and F. How is it matching?
In the second UV thing.
Thank you. Thank you. The whole thing was, yeah. So let me simplify the UV thing. I'll just write the UV thing entirely in terms of NC. Okay, so it's minus 2 NC to the 4 plus NC squared into NC plus 1, the whole thing squared, minus NC plus 1, the whole thing squared. Okay, so it's minus NC to the 4 plus 2 NC cube plus NC square, but minus NC square, so the NC square cancels, minus 2 NC minus 1. Do you agree with this? Okay. Now this is UV. IR, we will do similar matching, so that IR is minus NC to the 4 minus NC cube, that was from that term, from here plus 3 NC cube, that was from this term, plus 3 NC square, again from that term, minus 3 NC square from that term, minus 3 NC from that term, plus NC plus 1 minus 2. Okay, so it's minus NC to the 4 plus 2 NC cube, this, minus 3 NC, minus 2 NC minus 1. Isn't it remarkable? There are two things remarkable. A, that it works, and B, that we managed to do it right on the blackboard. Okay. Excellent. You know, I wanted to go through all of this really in full detail for you. Just because I know when I was a student, people would say, you can do the anomaly matching and it works. And somehow it all felt like, maybe they can do the anomaly matching, but can I do the anomaly matching? I just want to show you that it's a very trivial thing. It's a very simple thing to do. It's not some rocket science, as they say. It's a simple thing. Yeah.
Okay, I think we should doubt about the first row.
First row, please go. There are NF flavors of psi in the UV, but SUNF is one of the symmetries we're keeping track of.
But U1B will be one for all the NF.
But that's not how we should think. You see, under the symmetries, it's fundamental of SUNF times charge 1 of U1B. Okay? That is accounted for in the 1 times 1. No, you see the NF is part of the symmetry transformation under SUNF. The fact that we got this 1 here accounted for that. It accounted for that because it was fundamental of SUNF. You know that 1 came from some Dynkin label of this representation. And that accounts for the fact that it's fundamental of SUNF. So all those have been accounted for. We've traced TATA under SUNF. The question is, how many fundamentals under SUNF of charge 1 under B do you have? Understand? And there are NC of them. Because there is nothing here that keeps track of UNC. So as far as this calculation is concerned, UNC is just a flavor index. We only care about how many different guys there were. Is this clear? Because we have taken into account the fact that it's fundamental under SUNF. You know, there's a trace TA calculation that we've done to get that 1. And that accounts for the full multiplicity under SUNF.
Yes, but in the other cases we have to include the NF.
Because SUNF was not one of the symmetry labels. So then those indices just went around for the ride and had to be separately counted. Is this clear? Yes, you just have to keep your wits about you and you get the right answer. I mean, if the duality is correct, you'll get the right answer. Okay, excellent. Fine. So I think we will end our discussion of
Various possible NF numbers like NF is equal to NC or NC plus 1. You are writing some potential which you are questioning that whether that is.
yeah. So for instance, in
And
the
you can't write for general, let's say NF is equal to NC plus Q.
exactly, this was the game. You know, the game is to try to guess what the UV behavior might be.
And there is no general.
We're going to give Seiberg's guesses for all of them. It will not, as you will see. Okay.
But the postman will work without any knowledge of what NF is in terms of NC, right?
What?
The post row will work for any general NF, right?
First row will work for any general items. That's correct. The UV, that's what you're saying? The UV always works. UV is uniform description.
No, he means the
If you keep that symmetry only.
But of course you have to have a place in your moduli space of vacua where the symmetry is preserved. So for instance, if you were an NF is equal to NC, we did not have that. So the thing didn't need to match. Okay? Or if you're an NF less than NC, the Affleck times Seiberg superpotential, its minima will not preserve this.
That's why there is an anomaly.
What?
That's why there is an anomaly.
No, that's why there's no check there. We can only check that the anomaly coefficients are match for those symmetries that the vacuum preserves. If the symmetry is broken, there's nothing to check. Because as far as the UV, in the UV description, there's that symmetry and there's an anomaly, but the IR doesn't even see it. We can't ask how do the fermions transform under these symmetries because there's no symmetry in the IR.
But, sorry, these checks we did for global.
Yes.
But let's say if we have global gauge,
Yes.
so our theory actually has a chiral anomaly. So can we match that in UV and IR and say that as a check?
Global gauge. Difficult. You meant global gauge.
So global gauge. So
Yes. Difficult because you see in the IR description there's no gauge.
obviously there's the anomaly gauge.
It's all in terms of physical fields. Now, you know, if you have a global gauge anomaly, the invariant thing to say about that is simply that there is no symmetry.
Yes, but can one say that how much the symmetry is broken, it matches in UV?
Yeah. Okay.
In IR, why did you say because they are singlets?
Because they're singlets under SU.
Can't we have
Yeah, it could be that your suggestion for what the IR is that the gauge fields play a role. But that's not the suggestion so far, right? The suggestion was just some superpotential in terms of gauge invariant chiral multiplets. Right?
so in IR, why do we only have singlets?
Why do we only have singlets? The idea is that the theory confines. The low energy dynamics knows nothing about the gauge degrees of freedom. You know, gauge theory, gauge symmetries are redundancies of description, right? They may or may not appear in the sense that there may or may not be fluctuating gauge fields in your description. We expect in confining gauge theories in the IR, there are no gauge fields. Right, okay, so Diksha wants to be able to characterize how much that symmetry is broken. Okay, So see, how do we characterize it? We characterize it by an anomaly equation which is del mu j mu is equal to number times f wedge f. So if you can keep track of that f wedge f, you should be able to match. Now you see that f wedge f was the coefficient of theta. So del mu j mu should be the derivative of the action with respect to theta. Now theta appears in lambda, because lambda to the power b naught was e to the power minus 8 pi squared by g squared plus I theta. So in some sense you can keep track of it by differentiating with respect to lambda. Okay, so another way of saying it is that if you assign lambda charge under this R symmetry, under this non-conserved R symmetry, you should find charge conservation. Is this clear? You'll have to work out the numbers to see what charge to assign lambda. So that I think would be the way of keeping track of it in the IR. That is that symmetry is broken, but only because lambda has a charge. Yes, I don't think there is any information you will get from that you could not have got from the conserved R symmetry. Okay, but I think this would be another way of getting the Affleck-Seiberg superpotential, for instance. Demanding that the Affleck-Seiberg superpotential was invariant under the old R symmetry, provided you assign lambda a charge. But that will be the same thing as saying it's invariant under the new R symmetry. So I don't think that's somehow clearer to deal with something that's actually a symmetry. But I think it's equivalent. Please go on.
So if we take old R symmetry, then you are saying we should give charge to this theta also, so that.
Yeah. So let me say this in equations. You see, what we have is del mu j mu is equal to some number times f wedge f. What? That the statement that the current is anomalous means this number is non-zero. It's for the old U1R, the thing that was not really a symmetry. Right? This is what we will get from calculating the anomaly. Okay. Now, therefore, violation of R charge, delta of R charge, by integrating this equation over space-time, will be equal to this number times integral of f wedge f in units where f wedge f integrates to an integer. It's this, now in the same units are the way we multiply with theta. Okay, so this here is number times del by del theta of e to the power minus s. Okay? What is the advantage of this saying this rather than this? The advantage of saying this is that we now have a right-hand side that makes sense even when you're right, even when the description does not have a gauge field in it. Because even if the description does not have a gauge field in it, it will have the physical parameter, namely lambda QCD. Okay? Now, what is lambda QCD? There's this relation, right? That lambda to the power this b naught is equal to e to the power minus 8. I can't never remember these numbers, but 1 over g square plus I theta. And therefore, differentiating with respect to theta is same as logarithmically differentiating with respect to lambda to the power b naught.
Okay? This is the same thing as saying that we should assign lambda to the B naught some appropriate charge under R symmetry. If we do that, R symmetry will be conserved. So all terms in the action will have add up to 0 old R symmetry charge, providing lambda is associated appropriate charge. I won't try to do the algebra here to get what number and so on. But it's clear you can do it, right? Right? So that's another way of working, which I think will be just exactly equivalent to imposing true R symmetry charge. Right? It has the same data in it, because that number was how much we had to shift the old R symmetry in order to get the true R symmetry. So I think it will just be exactly the same.
But what does it mean by saying that lambda QC has a...
It's a formal device. It says every term in the action violates charge in a way that you can predict by seeing how many powers of lambda there are in that term. It doesn't mean anything real. It's not like lambda has a charge. But it's a way that allows you to ask how much charge is violated in individual terms of the action, provided you know effectively the dimension, right? Because lambda keeps track of dimension.
And this will help in finding anomaly in the IR because we don't have gauge field in the IR, is that the point?
Yes, exactly. Because we can't explicitly say f wedge f. It doesn't mean anything.
Right.
Okay?
We have lambda.
But we have lambda because that appears, it's a physical parameter, so it appears. I want once again to emphasize that we are using holomorphicity. Because we knew the theta variation, if there was a term which was mod lambda square, we would know nothing. This holomorphicity is all over the game, in every way of thinking of it. Okay? Excellent. Any other questions or comments? Go on.
You have to integrate f with this such that it becomes an integer.
Yeah. So, in the QCD action, we write theta times some number times integral f wedge f. And that number is chosen so that that number times integral f wedge f is always an integer. That's why theta has periodicity 2 pi. Okay? So, that's the usual convention of writing QCD actions. With that convention, this is what works out.
So, you can integrate f with just on any space we like.
On any manifold you like.
And that number will take care of that by making the whole thing an integer.
I didn't understand. The f, I can't remember the number, but let's say it's 1 over 32 pi square. Okay. Say it's 1 over 32 pi square times integral trace f wedge f is always an integer on any manifold. Now, if you're going to ask me, does it also work on a non-spin manifold or not? Maybe it sometimes becomes a half integer. Do you know, Diksha?
For even dimension manifold, it's
Always an integer. Okay. Okay, excellent. Yeah, so I suppose it had better be, right? Otherwise, theta would have a higher periodicity. Right, that's why theta is the same as theta by plus 2 pi. Okay, other questions or comments? Okay, go on.
So in the IR, how will you include lambda?
Lambda appears, look, it appears in the superpotential, for instance. Yeah, the superpotential had det m by lambda to the power b naught. Okay? So this would be a way of doing what Diksha wants. You see, det m would not have charge 2 under the old R symmetry. But lambda to the b naught also carries some charge by our new rules under the R symmetry. Total up, it will become 2. I somehow suspect that lambda to the power b naught has charge 1 by these rules. So I won't swear by it. Because it sounds like from what I said. I wonder in this case, yeah, let's quickly check that. In the case of NF is equal to NC, what is the old R charge of det m? So the old R charge is, let's see. Psi q has charge -1. So det m has some huge charge. Yeah. So det m has charge nf squared into minus, nf into -2. Minus nf into -2.
Sorry, M is uncharged under R symmetry.
What? No, M is uncharged under baryon symmetries. Charged under R symmetry.
There is no charge under R symmetry.
Q?
M is Q tilde.
Oh, yes. He's right. Yeah. Q. The fermion has charge, but we're talking about the boson. Right? So M is uncharged under R symmetry. Okay, so then this lambda by to the power B naught carries charge 2. 1 over lambda to the power B naught carries charge 2. That's what you will get when you go through it. Okay, excellent. Thank you. Okay. Perfect. Yeah, in fact, always the Fleck-Dine-Seiberg superpotential is like that. Because as Chintan pointed out, always det m has no charge under that R symmetry. But it always comes with the lambda to the power B naught. So that lambda to the power B naught carries that charge too. So that's your rule if you want. Okay, excellent. Other questions or comments? Perfect. So let's move on. Now let's look at NC greater than NF plus 1. What's the deal here? Okay. Okay, there are two ways to start this discussion. Let me start it in slightly the more physical way. Let us remember that at NF is equal to NC. Do you remember the coefficient B naught we had somewhere? B naught is equal to 3NC minus NF. So B naught, this function, the coefficient that appears in the beta function, is equal to 3NC minus NF. Okay? This tells us that if NF is less than 3NC, the theory becomes weakly coupled in the UV, strongly coupled in the IR. Theory is well defined as a deformation of a basically free theory in the UV. Okay, and seems to flow to strong coupling in the IR. Okay, on the other hand, if NF, okay, is greater than 3NC, then the flow is reversed. The theory flows to weaker and weaker coupling in the IR. Okay, and what it becomes in the UV, hard to say. You would have to find a fixed point that flows to this. Okay, so if NF is greater than 3NC, and we ask for the effective IR description, firstly the question is not terribly well defined, because there's no quantum field theory defined by the Lagrangian of n equals 1 QCD with 3NF, with NF greater than NC, because you have to know, we're not specifying the UV behavior. Okay? But suppose we've got some UV definition, which at some scale becomes the supersymmetric Yang-Mills theory with NF flavors, and NF is greater than NC. Suppose we get something like this. Okay? Then we can ask now, at lower scales, what is the IR behavior? The answer is very clear, right? The IR behavior is just free. Okay. So, for NF greater than NC, there's no mystery. NF greater than 3NC, there's no mystery. No mystery. The question is not terribly well defined, but if you give some appropriate meaning to this question, theory is free. Okay, the theory is free, and the low energy theory is made up of free quarks and gluons interacting in an essentially free manner. You go to higher and higher energies, start building up some interaction. Okay, there's nothing more to say about the theory. We don't. So what the question is not very clear in this case. But if you give suppose you find some fixed point such that some UV description such that you have you flow from there to at some intermediate scale and you get this description. Then at lower scales we want to know what is the effective field theory of this thing, and the answer is of course that it's just free. Okay, so here you don't need cyborg wizardry here. Everyone knows the answer. It's a free theory. Okay, fine. Now what about NF just less than 3NC? Just. What does the statement mean? What do I mean by just less than 3NC? If NC is 2, so 3NC is 6, is 5 just less than 6? You see, these words, just less, have no meaning at finite values of NC and N. But there's a place where you can give it meaning. That is, take NC large and NF large. Okay? Then, by varying NF over integers, we can make NC minus NF, 3NC minus NF divided by 3NC, the fractional change arbitrarily small. Okay, so that's what I really mean. What I really mean is we are going to large values of NC, large values of NF, and then making the fractional difference between NF and 3NC, or NC and 3NF, small compared to 3NC. Fractional difference meaning that difference divided by 3NC. Okay. Then, what can we say about the low energy physics of this theory? Okay. So, I've sort of mentioned this before, but let me say it again. Okay. In this case, the beta function d by d log lambda is most naturally written not in terms of the variable g squared, okay, but in terms of the variable nc times g squared, the 't Hooft coupling. Okay, in this variable you get terms of equal order in nc at first, second, third, fourth order. Okay, so we get d by d log lambda of this 't Hooft coupling, lambda which is nc times g squared. Okay, this has at leading, of course there's no linear term in lambda because the operator classically has dimension 4, it's marginal. Okay, when there is going towards the UV, this log lambda is motion towards the UV, the theory gets more weakly coupled. That's asymptotic freedom. And the coefficient for that is nc minus 3nf divided by nc times some number order 1. Okay, times lambda square. Thank you. You can say divided by 3 now. 3nc doesn't make a difference because I've got a number. This number is a positive number. Okay? And then we've got a lambda cube correction to this. Okay? And then the lambda cube correction is some number order 1. This is anomalously small when NF is equal to 3nc. And some number which is of order 1, neither particularly big nor small when NF is of order 3nc. All these, everything I'm saying here is known very precisely. Okay, I'm not saying it precisely. And positive. Positive, let's call it A times lambda cube. What? There is a plus sign. Oh, there's a plus sign. And plus there is lambda to the 4 and so on, which we're not keeping track of. Okay. Now, let's look how the renormalization group flow. Let's look how the renormalization group flow towards the IR happens in such a theory. This was the beta function for flows towards the UV. If you want flows towards the IR, you have to flip the sign of the right hand side. Okay. This tells us that if we start with some lambda, it increases. This is simply the statement that lambda becomes strongly more and more strongly coupled as we go to the IR. But there is this term. Okay? So these two cross at some point when this equals this. And then the flows are like this. Is it clear what I'm drawing? It's not clear. This axis is lambda, and flows are flows, RG flows towards the IR. So if you start from a small value here, you will be driven to this point. You start from a bigger value, you will also be driven to this point. Okay, but now some of you are thinking, this is sort of crazy. What about the lambda to the 4 term? Can't it change that diagram? And the lambda to the 5 term? And in general, of course, you're right. But let us suppose we're working in the place where NF minus NC, NF minus 3NC divided by 3NC is equal to epsilon is very small. In this case, where this fixed point occurs is where we're balancing epsilon lambda squared versus lambda cube. So it occurs at lambda of order epsilon. Now, where this balancing happens, this term and this term are both of order lambda cube, epsilon cube. But a lambda to the 4 term would be of order epsilon to the 4. And a lambda to the 5 term would be of order epsilon to the 5, and so on. So in the limit epsilon goes to 0, it is allowed to ignore all the higher terms. By making, in a controlled approximation, we can controllably ignore the higher terms. So this picture, we know is correct at small enough epsilon. In fact, in the limit epsilon goes to 0, this fixed point goes here. And so reaches the free theory. So what have we deduced from this analysis? From this analysis, what we've deduced is that at epsilon small, which means NF near enough to 3NC in fractional units, our IR behavior is at a fixed point of the renormalization group. And therefore, our IR behavior is a conformal field theory. Moreover, at epsilon small, it's a very weakly coupled conformal field theory, because the effective coupling constant is controlled by this lambda, which is very small. Is this clear? Note that this is extremely different from the IR behavior we have postulated so far. Every time so far we've postulated the IR behavior as that of confinement. Oh, by the way, there's something I didn't say about NF is equal to NC plus 1 that I should say. But first, let me complete this discussion. Okay? Confinement, mass gap, up to, maybe there's no mass gap, maybe there are these massless fields, but these massless fields all are massless fields of spontaneous symmetry breaking or something like that. Very weakly coupled Goldstone bosons. Here we are saying that the low energy, the low energy theory would be effectively a free low energy theory of Goldstone bosons. That would be the claim in dimensions when NF is equal to NC or NF is equal to NC plus 1. Okay. Here we are saying that the low energy theory has some version of weakly coupled quarks and gluons floating around. And the theory is interacting even in the deep IR. It's not a free theory. It's a very different idea. It's a conformal field theory, non-trivial CFT in the deep IR, not a free one. Is it clear that we're making a qualitatively different claim for the IR behavior? Yeah. Moreover, there'll be some sense, maybe approximate, in which the theory has gluons in it. Because in terms of the quark and gluon degrees of freedom, the theory is weakly coupled.
If epsilon is small but finite, then is this property?
Yes. So if epsilon is small but finite, of course here you need to make a leap of faith. But if epsilon is 0.0001, the coupling constant of this theory will be 0.0001. So unless one of those other coefficients of lambda to the 4,
I see, it's in that asymptotic
asymptotic thing, but unless one of those other coefficients had some anomalously high value, it would be very unreasonable to suspect that this was not the case. This kind of question we can ask for QED, right? QED we can do perturbation theory, but in real world alpha is 1 over 137. Usually it works out, right? Small enough.
I was just trying to ask that you did NF is equal to NC and NC plus 1, and then you had gone to this. And is there any
in between
difference, or between also these are similar kind of potentials, and then
no, we'll see. By the end of these lectures, you will have a full picture of all values of NF. I've jumped, I agree. You might have thought I should do NF is equal to NC plus 2. I've jumped because there is another end where we already know the answer. Okay? I will come back to all values of NF. So we'll just hang on. Okay? So here we already know the answer. Okay. So now, what can supersymmetry, a very similar analysis you could do in pure QCD. Pure QCD also, similar analysis works. Similar conclusion follows. So even in pure QCD, there is a certain number of flavors of fundamental quarks. If you go beyond that, you lose asymptotic freedom. If you take NC and NF large and you go tuned to that fixed point, once again you have an epsilon. Once again a similar analysis, the sign of the two loop term is the same. And once again, we know that pure QCD also has conformal behavior at large enough number of flavors. Okay, has supersymmetry bought us anything here? Actually, it buys us something quite nice. And this now starts making contact with the representation theory that we discussed, and you might have forgotten, for superconformal field theories. You see, because now, in our theory, we have supersymmetry and conformal invariance. So we have superconformal invariance. Okay. Now, if you remember, we spent maybe 3 or 4 lectures discussing how in superconformal field theories, you have unitarity bounds. We discussed superconformal representation theory and so on, right? There were these general representations, there were short representations, all representations had some unitarity bounds, and short representations saturated them. Okay. Now, one of the unitarity bounds goes as follows. You have to get your normalization straight. But working with the normalizations that we're working with here, if you look at D equals 4, N equals 1 theories, you remember the superconformal algebra. The superconformal algebra there was SO 4, 2. Then there was an R charge, just a single U1 R charge. And then there were the supersymmetry operators and their S's. Okay. Now you remember that there were various supersymmetry bounds, one of which went this way. One of which went that the scaling dimension, let me call it D, of a scalar operator charged under R symmetry is less than equal to 3 by 2 R. Okay, we didn't actually derive this one. We derived various samples. We didn't actually derive this one. This is actually an easy one to derive. R is the R charge, and you have to ask how that R charge is normalized. Now the R charge is normalized so that Q's have R charge 1. That is the same normalization we've used because theta had R charge 1. Okay? With that normalization, D is less than equal to 3 by 2R. The scaling dimension of any scalar operator, sorry, greater than equal to, any scalar operator in the theory has to be greater than equal to 3 by 2 times its R charge. Okay. Moreover,
this is the bound for this example.
For superconformal field theories, it's a bound that comes from algebra. Example is not important. As long as you have D equals 4, superconformal algebra, n equals 1, this bound is always true. Okay? Moreover, you can ask what kind of multiplets saturate this bound.
So is this R charge the true R charge, which is the
True R charge.
conserved one?
True R charge. Because algebra only cares about true symmetries, right? It does, if there's some symmetry in your head that was broken, algebra doesn't care about that. This is the algebra R charge that appears in the superconformal commutation relations. And it had better be conserved, otherwise superconformal algebra is not a symmetry of your theory. Clear? Okay, fine. So we have this bound. Moreover, I don't know if you remember, can you remember, for instance, we worked out the bounds for currents in a conformal field theory. And we found that J in a conformal field theory had to have dimension greater than equal to D minus 1. And that this was saturated only when del mu of J mu was equal to 0. Okay? Because short representations have null states. Null states are not there in the representation. That becomes an equation of motion or some equation for the operator. Okay? Good. Okay, go on. What? Q has naive R charge of 1. No, but it always has R charge 1. You see, because
It doesn't have baryon.
the R charge, true R charge was some mix of a flavor charge and true R charge. There is no flavor charge. Okay. What I wanted you to remember was that when bounds are saturated, there is an equation that you write. Now, this equation, this bound is saturated when either Q or Q bar, but in this particular case, Q bar on operator is equal to 0. Okay? But Q bar on operator is equal to 0 is an equation that holds for the highest or lowest component of a chiral multiplet. Because a chiral multiplet obeys the condition D bar on that chiral multiplet is equal to 0, and D bar differs from Q bar only by some del by del theta bar. Okay? So, up to some del by del theta bars, that's same as Q bar is equal to 0, and the first component has no theta bar, the lowest component has no theta bar, so it's annihilated by Q bar.
It differs by del x.
Del by del x times theta bar. Times theta bar. It doesn't matter for the first component. Yeah, sorry, del by del x times theta bar. Okay? So this equation, if you've got a chiral multiplet and it has R charge, we know that it must saturate this inequality. Okay? that it must saturate this inequality, just like a conserved current has to saturate the inequality. Its dimension has to be equal to d minus 1. Okay? Now, we've been dealing in our discussion with all these chiral multiplets. Okay? In particular, Q is a chiral multiplet, Q tilde is a chiral multiplet. M, this gauge invariant operator, Q tilde that we've been talking about, is a chiral multiplet. Okay? So, in the case of the example we've been studying, let us remember R charge of Q was equal to 1 minus NC by NF. Okay? R charge of Q tilde was equal to 1 minus NC by NF. When we discuss bounds like this, we're only allowed to talk about gauge invariant operators. Things you can insert in the path integral. Okay? So, let's look at the R charge of M. This is equal to 2 into 1 minus, so let's write it as NF minus NC by NF. Okay? And so we have a prediction that comes immediately from symmetry. The prediction is that the dimension of M, of this gauge invariant operator M, is equal to 3 by 2 times 2 times NF minus NC by NF. Okay, is equal to 3 into NF minus NC divided by NF. What have we done? We put together three things. A, the knowledge that our low energy theory is conformal, at least when epsilon is small, therefore superconformal. B, the knowledge that M is a chiral multiplet. I mean, that operator M is the first term in a chiral multiplet, therefore is annihilated by Q bar. C, the knowledge of superconformal representation theory that tells us for all such operators have to have dimension 3 by 2 times R. And we've come, putting them together, we've come up with this prediction.
So the second question, how is M the fundamental field I am now?
How is M the?
One of the fundamental fields.
It's not one of the fundamental fields, but it is a gauge invariant operator described by a chiral multiplet. We're not allowed to talk about dimensions of non-gauge invariant operators. Those don't make sense. Insertions in path integral have to be gauge invariant. Right? I suppose you could ask, the fact that Q was fundamental and Q tilde was fundamental, does it, Q was chiral and Q tilde was chiral, does it mean that M is chiral? Classically, surely yes. I suppose you could ask whether quantum mechanically there might be a problem. Let's say we assume that's not an issue. You know, that kind of worry you might have. But let's assume that it works out. Okay?
So this is the dimension of thing which is just scalar, first scalar.
The dimension of the scalar part of M. Yes. Okay, and then the dimension of all the fermions and so on follow. The fermion will be half more than this. Okay? Louder. What is equal to 2? Why is D equal to?
We are looking at that NF very close to 3 and
Ah, good. Correct. So the first check we want to do of this idea is this. Suppose we first look where Kanu wants to look, near epsilon equals 0. There we already know what the dimension of M is. Because the theory is very weakly coupled, so the dimension must be that of phi, I mean Q times that of Q plus Q tilde. But if Q and Q tilde were free fields, each of them has dimension 1. So the dimension should be equal to 2. But as Kanu points out, if NF is set equal to 3NC, then we will get 2NC divided by 3NC into 3. So we will get 2. So this is a sanity check of this point. That in the free limit, It has the answer we expect. But as we go to the interacting theory, this number starts decreasing. Because NF starts decreasing.
Interacting means epsilon non-zero.
Epsilon becoming bigger and bigger. This number starts increasing. So now let us see how far our picture of the low energy dynamics could possibly be true. What is the test? Well, I don't know if you remember, but one other thing that we had proved when we were discussing conformal representation theory is that in 4 dimensions, every scalar operator has to have a dimension greater than or equal to 1. And if it has dimension 1, it has to be a free theory, a free operator. Do you remember this?
That will saturate the bound by square.
Exactly. So now we know the dimension of this, and we can ask, when does it obey this is greater than or equal to 1? Okay. So 3 NF minus NC by NF is greater than or equal to 1. If we want this implies 3 NF minus 3 NC is greater than or equal to NF, which implies that 2 NF is greater than or equal to 3 NC, which implies that NF is greater than or equal to 3 NC divided by 2. So what have we concluded? We've concluded that our picture for what is going on in the IR of this theory cannot be true for NF less than NC by 2. 3 NC by 2.
So if the dimension of n is the free theory of string,
No, it was 2 in the free theory, and it can become less than 2 in the interacting theory.
but then we are saying greater than 1, the one which is equal to 1 is also situated in the free theory.
Is also saturated in a free theory, but in a different kind of free theory. In a free theory where M would be one of the free fields, not a Q-cuber. Right? M was in the original free theory a composite of 2. Okay. Now, actually one of the things, so let's suppose we are at numbers such that 3 NC by 2 is an integer. So that NF can be equal to 3 NC by 2. So first thing we've got is the idea that this Schumann was asking, how far down in epsilon can this picture go? Certainly it cannot go below this. Okay, so the idea that we have this conformal window of dynamics cannot be true for NF less than 3 NC by 2. Okay, and if it extends all the way down to 3 NC by 2 as we are going to conjecture, then at 3 NC by 2, this field M becomes a free field. So at least it becomes a free field. May even be that the whole theory is free. Okay? NF is equal to 3 NC by 2, somehow very interesting point.
So for NF near 3 NC we have quarks, and for NF equal to 3 NC by 2 we have this free.
This thing. You see what's happening is that this fixed point is going to, as epsilon increases, so as NF goes down, fixed point is, coupling is becoming stronger and stronger and stronger and stronger. But we are going to postulate that the theory remains conformal. Okay? But the fixed point stops existing when NF hits 3 NC by 2. Okay, the IR dynamics is not governed by a fixed point of is not conformal anymore when NF is equal to 3 NC by 2. As we go towards 3 NC by 2, the coupling constant of our conformal field theory is becoming stronger and stronger and stronger. So we're going further and further away from free quarks and gluons. And then somehow it becomes so strong that something happens. And the conformal theory gets destabilized. Maybe its vacuum becomes unstable, whatever. Something happens.
But at NF equal, when when dimension of M becomes 1, can we say it's free mesons or something, or we cannot say?
M becomes a free field. Perhaps the whole theory becomes free. But what it is, we will say many things. Hang on for 2 minutes. We will try to provide a dual description of this. In fact, we will have a dual description. We will say some things about it, but hang on.
The dimension of charge is like half.
What?
The dimension of charge becomes half when it reaches 3 and 0.
Dimension of what?
Charge, Q.
Oh, Q. But Q is not a good operator in the theory. Q is part of our description of the theory. There is no gauge invariant correlation function that allows us to measure the dimension of Q.
And that formula D greater than
Only applies to proper operators, so gauge invariant operators. You see, because the whole unitarity analysis works using the state operator map. And states are always gauge invariant, because states are states on an S3. Gauge indices have to be saturated. You can't put a charge on a sphere. Okay?
In the previous case,
Yes.
NC, previously you said NF is equal to NC plus 1.
Yes.
And if you look at that theory for NC is equal to, let's say, 2.
NC is 2. Let's look at NF is equal to, very good. So, if we take NC equals 2 and look at the theory,
NF is equal to NC plus 1. You just,
so that's 3 by 2. That's 3 by 2. That saturates this. Excellent question.
I'm saying do it exactly instead of looking at the puddles.
So Shuman's asking, for this case, 2 different descriptions have to be the same. It's similar, you see. In fact, good. So this, you see, what we have there is a theory of Goldstone bosons, which is a theory of massless particles, but those that are free. So this suggests that this idea that the whole theory becomes free at this point, this gives some evidence for that. Because all we're saying is that it's some conformal field theory. Okay. However, there's probably more to say about your question. It's a very good, I never thought about it. If you take NC equals to, of course, if you take higher values of NC, they won't overlap. So this is one very particular case. I'll see if there's something more to say about your question.
that picture is not valid for NC.
The perturbative picture is not valid, but we are going to propose that there is a conformal field theory all the way down to NC, 3 NC by 2. And that is going to be our proposal. It should be strongly interacting from the point of view of quarks and gluons. But it could be weakly interacting from the point of view of other, often happens in conformal. In n equals 4 Yang-Mills theory, G is equal to infinity is same as G equals 0, right? It becomes weakly interacting in terms of other variables. Right, okay. This is of course a very tantalizing point, but anyway, it's 1:40, we won't get lunch, so we better stop. In the next class, okay, so Diksha will hope with, if her preparations go well, on next Friday she will tell us about instantons and connection with this stuff. Next Tuesday before that, we will try to discuss more about this picture for NC greater than NF, 3 by 2, greater than equal to 3 by 2. And the really interesting thing is this proposed new duality. And that will also tell us what is the physics between NC plus 1 and 3 by 2 NC. Okay. So hopefully by the end of the next week, our discussion of n equals 1 Seiberg dualities will begin to come to an end.